Okay, so the recording has started. Okay, so good evening, everyone. My name is Chandan Kumar Gupta. I'm a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I'm your NPTEL-PMRF Teaching Assistant for the course Probability and Statistics. This course is offered by Professor Somesh Kumar. He's a faculty in IIT Kharagpur. So this is the 10th week of problem solving session. Okay. So up to this point, is there any doubt or you people have any queries? You may ask here or after any time on my YouTube channel or somewhere else. Okay. So is it okay now? Like up to this point, everything is fine. And is my screen and my voice as perfect here? Anyone?
Yes, sir.
Okay, thank you. So let's start. So up to week 9, we have discussed many things like uh, from week 1 to week 8, we have mainly discussed about the probability theory part. Okay, the random variable, the definition of probability, the discrete and continuous random variable, and the transformation of random variable, the moments, etc. Okay. Uh, Now in week 9, we have discussed about the statistical inference, the introduction to statistical inference. There we have mainly discussed the point estimation techniques. Okay, what is estimator, what is estimates, and all these things. So mainly these are like statistical inference. Okay, so today we will mainly discuss like the sufficiency or sufficient statistic, then confidence interval, or interval estimation. Let's say. Okay, these are the two topics that we will discuss today. So let's start with the sufficiency. Like you people may remember that good statistics had mainly 4 different properties. That is unbiasedness, the consistency, efficiency, and sufficiency. Okay, so these are mainly four properties of a good estimator. Okay, so let's start with efficiency. Okay, suppose we have let T1 and T2 be two estimator or a parameter or function of parameter. Suppose I say theta. Okay, so the variance associated with those estimator or those statistics. Okay, let with T1 it's T1 VT1 and with variance T2 it's VT2. Okay, now if I say or I assume that variance of T1 is greater as compared to the variance associated with the estimator T2. So in that case, we say that T2 is more efficient than T1. Okay. So overall, the main thing is, suppose we have more than one estimator or more than one statistic for a parameter. Then out of those estimators that have minimum variance is efficient estimator. Okay. So the next is like most efficient estimator. Okay. So efficiency is like all of those estimator, the variance which have the minimum variance is more efficient. The simple thing. The most efficient estimator is like in the class of unbiased estimator. Okay. In the class of, okay, sorry. In the class of consistent estimator. In the class of consistent estimator, the estimator having the minimum variance the estimator having the minimum variance is called most efficient estimator. Okay. So obviously that means suppose let's denote it by T. Okay. Then efficiency is like defined as efficiency of an estimator is defined as variance of the most efficient estimator divided by variance of any other estimator from the same consistent class. Okay. From the same class of consistent estimator. This is called the efficiency. Obviously, you may find out that it is always less than or equal to 1. Okay. The next is sufficiency or sufficient statistic. Okay. So again, like we have samples. Okay. We have samples because these are the sample property. Na? Like unbiasedness, sufficiency, efficiency, and consistency are the sample properties. Okay. So that means what? That means suppose I have a sample and for those sample, I have an estimator. Okay. So that means the estimator represents the whole sample. Okay. So the sufficient estimator is defined as those estimator that has the same amount of information which is included or which contain in the sample as well. Okay. So this is the sufficiency. This is just a rough definition, a raw definition. The actual or standard definition is like, suppose we have like x1, x2, xn be a random sample from a population with some, suppose from a population with p theta, where theta belongs to the parameter space capital theta. Then a statistic t, which is nothing but a function of tx, obviously, those random sample. This is said to be sufficient if if the conditional if the conditional distribution, if let me write, if the conditional distribution of x1, x2, xn given t, given the statistic t is independent of the parameter theta. Here I have considered the parameter theta. So that is the conditional distribution of the random sample given the estimator t is independent of the parameter, then that estimator is termed as the sufficient statistic or sufficient estimator. Okay. Or the note is like this sufficient estimator is mainly used for the reduction. Okay. For the reduction of the dimension. How? Like, let me write. It is actually a data reduction technique. And the meaning of this is like, suppose I have x1, x2, x3, x4, x5. So I have a sample, 5 samples. So that means I am dealing with the 5 tuples kind of data. Okay. And all the information that contain with the x1, x2, x3, x4, and x5, the same amount of information is contained in a sufficient statistic T. For example, summation xi here. Okay. So summation xi have same amount of information as x1, x2 up to x5. Okay. So instead of using xi, I can use summation xi because both have the same amount of information in related to the population. Okay. So we are like here, we reduce the data dimension. So this is actually the data reduction technique. Okay. So like, for example, suppose we have x1, x2, xn random sample which follows Poisson lambda distribution. Okay. So that means what? For Poisson lambda, okay, let me write like this. Probability that x equal to e to the power minus lambda, lambda to the power x upon x factorial, lambda is greater than 0, x is greater than 0. Okay, this is given. Now I have x1, x2, x3, x4, x5. I can directly use summation xi I from 1 to n. Suppose this is our tx. So actually this is our sufficient statistics. Okay. We will solve some numericals. Okay. Just I am telling you here that I am going to either consider x1, x2, xn samples or directly summation xi. Okay. So both have the same information for the population parameter or for the population from the Poisson parameter. Okay. So that means this summation xi is sufficient or enough to for our analysis purpose kind of thing. Okay. So this is the data reduced. The data here is reduced or the dimension is reduced. Okay. So that's why the sufficiency is also termed a data reduction technique. Okay. Now the next is like there is a definition. There is one more definition because this definition is like what? Suppose T is an sufficient statistics, then the conditional distribution of x1, x2, xn given T is independent of parameter. So we have one more kind of thing, a theorem form that is called Lehmann-Scheffe factorization theorem. Usually we call it as Fisher's like factorization theorem. Okay, so Neyman-Fisher factorization theorem. What it states actually, it states that the joint PDF can be write down as like here. Suppose we have x1, x2, xn, x1, x2, xn. These are the IID random sample from the PDF, for example, fx theta. Okay, so is there anyone who want to ask anything? Okay, no problem. So, okay, the thing is key, we have x1, x2 up to xn random sample, and these random sample are taken from a population fx. Okay, now the joint distribution is defined as, suppose, let me write it with L theta, which is the product I from 1 to n fx I theta. Okay, okay, so this is the case. This is our joint PDF. then this joint PDF can be rewritten in the form of like G of Tx theta into Hx. Okay, so this can be factorized in two functional form. The first one is a function of the parameter and the sample, a function of sample, random sample, and the another one is the only a sample of random sample and which is independent of parameter. If we can write the joint distribution in this form, then this Tx, this Tx is termed as the sufficient statistics or sufficient estimator. Okay, so this can be used to check whether a statistic or estimator is sufficient or not for the given parameter. Okay. Also, we have one more notes actually. If like the maximum likelihood estimator that we have already discussed in the last class, suppose if it exists, okay, are the function of sufficient statistics. Okay, MLE, if MLE exists for a parameter, then this is the function of sufficient statistics. This is one note actually. Okay, or you can also like okay, there is one more thing, like if sufficient statistic is always consistent in nature actually. Sorry, not sufficient, the MLE. The MLE is always consistent. Okay, so MLE is always consistent estimator. Okay, so these are some of the properties related to MLE and sufficient statistics. Now there is one more thing. We have discussed unbiasedness, sufficiency, and consistency. There is one more thing that I have already told, the completeness property. The completeness property of an estimator. Okay. Again, suppose X or Xi belongs to some parameter, some population P theta, where theta belongs to the parameter space, capital theta. Then we say that the family of distribution, okay, the family of distribution, let me write it with P, cursive P actually, P theta, such that theta belongs to capital theta is complete if and only if, like it's like the expected value of any function equals 0 for all theta belongs to capital theta. This implies the probability that it is 0, that the function itself is 0 is actually 1. Or we can say that, or in simpler form, I can say that if expected value of the function comes out to be 0, then this implies the function itself 0 actually. Okay, so this is the properties of completeness. Okay, suppose expected value of a functional form of a random sample is 0, then this implies that estimator itself is 0. Okay, if this property holds, this is the case for the completeness. Okay, complete statistic. We have many questions related to all those topics actually. Okay, so yes, now we have two theorems actually. Okay, with the help of these above properties, we have two theorems. The first theorem is like Rao-Blackwell theorem. Okay, this theorem is mainly used to find the UMB UE, okay, uniformly minimum variance unbiased estimator. Okay, this theorem mainly gives the uniformly minimum variance unbiased estimator. Okay, how it gives, like, for example, let me write the statement. The small statement is this. Let, for example, dx. Okay, let dx be unbiased for function of parameter. Okay, there d theta, and let t be a sufficient statistic. Okay, then here uniformly minimum variance unbiased estimator, that means that estimator which is unbiased and have minimum variance in the class of those unbiased estimator. Okay, which that is the case. Okay, that is going to be a candidate for the UMBU. Okay, so here dx be unbiased estimator for g theta and t be a sufficient statistics. Then ht, okay, ht function of the sufficient statistics, which is equal to expected value of dx given t is unbiased for g theta, and and its variance is either less than or equal to variance of theta dx for all theta belongs to the parameter space capital theta. Here you can see, dx is an unbiased estimator, okay, and t is a sufficient statistics. Then a function of the sufficient statistics, which is ht. This is nothing but the function of the sufficient statistics. This, which is defined as the expected value of dx given t, this is unbiased for g theta, and the variance of this ht, is either less than or equal to the any other unbiased estimator. Here, this is what? V theta dx for all theta belongs to capital theta. That means for any unbiased estimator, the variance of ht is always less than or equal to. So that means what? It is unbiased and have minimum variance. So that means ST is our minimum variance unbiased estimator. Okay. So this is the case. Now there is one more theorem actually. The last theorem, that is Lehmann-Scheffe theorem. Okay. So this theorem, here one more condition is added. The properties of completeness is also added here. Like let T be a complete and sufficient statistics. Okay. Here, let T, let's suppose we have a random sample x1, x2, xn from a population T theta or fx theta. Okay. And let T be a complete and sufficient statistic. Okay. T be a complete and sufficient statistic. Okay. Then ht, again the function of t, is uniformly minimum variance unbiased estimator for its expectation, sorry, that for its expectation g theta, which is equal to like expected value of theta h of t. Okay. So this is the case. Okay. We can find the uniformly minimum variance unbiased estimator then from with the help of the sufficient statistics. Okay. So these two theorems, that is Rao-Blackwell theorem and the Lehmann-Scheffe theorem, gives us the uniformly minimum variance unbiased estimator, which is Sorry, you are not audible. Hello.
Is less than or equal to T2.
Where less than or equal to? Sorry, I'm still not able to hear you. Your voice is quite low actually. Okay, you can type if you have any doubt. Okay. So this is the case. Okay. And up to this point, we have completed our point estimation part. Now the next one is the confidence interval part, the interval estimation or the confidence interval. Okay. So here it's like we call it the confidence interval because here there are some probability, the involvement of some probability terms in our the estimation technique. Okay. When we construct the confidence interval or the interval estimates is constructed by adding or involving some probability terms. Okay, so that's why it has some level of confidence. So the term confidence interval, it's known. Okay, so the thing is like what? In point estimation that we have discussed in the last class, we have a value, a single value which indicate the estimated value of a parameter. But here in interval estimation or in confidence interval, uh, we have a range of values, or we have two statistic actually. Instead of one, which directly denote the point, the value of the parameter, here we have two values, which between which our true value of the parameter lie. Okay, so that is called the confidence interval. So the thing is like, for example, again the same thing. Suppose x be a random variable, and we have x1, x2, xn random sample from the same distribution f x theta, and let t1x and t2x. In point estimation, we have tx. So here we have to consider two statistics. Na? So I have like we have considered t1x and t2x. These are the two statistics in such a way that the probability that this parameter or function of parameter lie within sorry, within this t1x and t2x. Okay, have some property, have some probability not equal to 1, which is 1 minus some quantity. Okay, alpha, here this alpha is termed as level of significance. Okay, this is nothing but the probability of rejecting the null hypothesis. We will discuss it in the 11th week class actually. Okay, type 1, there is a kind of error, type 1 kind of error. Okay, the same value, the on the basis of magnitude, it is same. Okay, alpha, the level of significance. Okay, the probability that rejecting H naught, rejecting some statement when that statement is true is alpha. Okay, so this 1 minus alpha is called our confidence level. Okay, and in percentage, we can say confidence. That is again the confidence interval. Okay, so the parameter value, the true value of the parameter lie within E1x and T2x. It has the probability 1 minus alpha. So this T1x, T2x is nothing but this is our confidence interval. Okay, with confidence at 100, 1 minus alpha. Okay, usually we take the value of alpha as either 1% or 5% or 10%. So on that basis, it is either 99% or 95% or 90% confidence interval respectively. Okay, so this is the case. We will solve some numericals based on these as well. Okay, so the next thing is like how to construct the confidence interval. So we have some more things under some condition. So like for normal distribution. Okay, CI, that is confidence interval for normal distribution. Okay, so let x1, x2, xn be IID random sample or random sample from normal, mu, and sigma square. Here mu I, sigma I square. I haven't written mu I and sigma I square. That means identical. X1 follows mu sigma square, X2 follows, Xn follows. That means, and these are random samples. So that means it is IID in nature. Okay. So Xi's are normally distributed random variable with mean, mu, and variance sigma square. Then we have conditions like we need to construct the norm. We need to construct the confidence interval for the parameter mu when sigma square is known and sigma square is unknown. And on the other hand, we can construct the confidence interval for the sigma square when mu is known and mu is unknown. So there are four possibilities we can think of. Okay. So let's start with the first case. The confidence interval for the parameter mu when sigma square is known. Okay, when sigma square is known. So as we know that since we need to find the confidence interval for mu, okay, and since we do not know the value of mu or the true value of mu, so what we can use instead of mu, the estimate of mu, that is sample mean x bar. Okay, because it's a population mean. So if we do not have the information of the population mean, we can use the sample mean there. Okay. So that means what? X bar. Now we know that if x1, x2, xn follows normal distribution with mean mu and variance sigma square, then the x bar also follows the normal distribution with the same value of mean mu, but the sigma square now changed to sigma square by n. It depends, inversely depends on the sample size. Okay. So this is the already we have discussed. Okay. Now we also know that one more thing that Z, which is x bar minus mu upon sigma by root n. This follows the normal distribution again with mean 0 and variance 1. That is Z is nothing but the standard normal variation. Okay. So up to this point, everything is clear because we have already discussed it many times. Now, now the confidence interval at Z minus plus Z alpha by 2. Okay. So this is the case Z nu by 2. This value is taken. This value is taken from the normal table. Okay. From the table Z at Z table, actually not normal table, that is Z table. Okay. Then sigma by 2n. Okay. So this is how we construct the Z nu by 2 into sigma by root n. So this is the level confidence interval at alpha level of significance. This is nothing but the alpha level of significance. I can tell you what is the meaning of alpha. Okay. So here you can see, suppose it's a normal curve, then we know that we have two statistics actually. There is one statistics T1 and one statistics T2. So let me take this one is T2 and this one is T1. Okay. And the probability that the true value g theta lie within this range is 1 minus alpha. And this is suppose alpha 1, alpha 2. Okay. And since it is symmetric in nature, we consider it like alpha by 2, alpha by 2. So from there, we use this z value at alpha by 2 level of significance. Okay. And then we construct this confidence interval at nu alpha by 2 level of significance. Okay. For the parameter mu. This is a simple formula for the case we need to know these values and then directly put the values taking minus sign and plus sign. We have lower limit and upper limit of the confidence interval. Okay. So this is the case. Now the next is what? Confidence interval for mu when sigma square is unknown. This case is when it's known, we can directly use the value of sigma square. But here, we do not know the value of mu and we do not have the information about the sigma square as well. But when I need to construct the confidence interval for mu, I can use the estimate of sigma square instead of sigma square. Okay. So yes, we know that the estimate of sigma square is as the sample variance. Okay, this is the population variance. So the sample variance is there. Also, there is one more thing. If this sigma square is not known, then in that case, this does not follow this z. Okay, then we use, instead of normal, we use t distribution. Okay, so at this point, the let me write directly. The confidence interval is like x bar minus plus t alpha by 2 and minus 1 time. This is the value tab we will take from the table. Okay. And minus 1 is the degree of freedom. When we have x1, x2 to xn sample, then n minus, we take the n minus 1 degree of freedom because there is a one parameter which is not known. So 1 degree of freedom is less. Then since sigma square is not known or sigma is not known, so we can use as and then by root. Okay, so this is the case when for the confidence in for the confidence interval of mu when we do not know the sigma square. Okay, again, if you may recall, you may find out that the z and the t both are symmetric in nature. Okay, the t distribution, the z distribution, both are symmetric in nature. There is one difference, and that is when we are talking about the z distribution, that is mesocortic in nature, but t distribution is leptocortic in nature with symmetric. There is no skewness involved in the t distribution. T distribution is symmetric distribution with leptocortic kurtosis. Okay, and z is mesocortic with symmetric. So we use t distribution here. That's why t alpha by 2 is taken instead of like 1 minus alpha by 2 and alpha by 2. Okay, we will see in the next like problem. So this is the case. Then the next problem is like the third one, confidence interval for sigma square when mu is known. Okay, the next case. So when the mu is known, the confidence interval of sigma square. Again, since we need to construct the interval estimate for the sigma square, this means uh, we need to use the statistic kind of thing of sigma square. Okay, and since we know the value of mu, so we can directly use the confidence interval is its summation xi minus mu, because mu is known here, I from 1 to n obviously, summation xi minus mu whole square. Okay, so there is some properties. Okay, in chi-square distribution, you people may read that it follows the chi-square distribution. Okay, with the degree of freedom, and obviously since mu is known, so the degree of freedom is n, no doubt. Okay, and the level of significance here, chi-square distribution is chi-square distribution is positively skewed, not symmetrical in nature. So I can't use alpha by 2 on both sides. So we can use its alpha by 2 and here 1 minus alpha by 2. Okay, or alpha 1, alpha 2. You can take alpha 1, alpha 2 in the same manner like Like in this case, okay. In this case, suppose in this case, what this is alpha 1 and this is alpha 2 and this is 1 minus alpha 1 minus alpha 2. Okay. And this value for chi-square distribution, I'm talking about the chi-square distribution now. For chi-square distribution, for example, this is chi-square, it's 1 minus alpha by 2 at n degree of freedom. And this is our chi-square alpha by 2 with n degree of freedom. Okay. So we construct the like two-way sample. So we take alpha 1 equal to alpha 2. Then in that case, it is alpha by 2. It is alpha by 2. And this area is 1 minus alpha because this is our definition. Probability that the g theta lie within T1x to T2x is 1 minus alpha. So we have considered alpha by 2 instead of alpha 1 and alpha 2. Okay. So that's why we choose this. Okay. Then again, when the fourth case, when sorry, confidence interval for sigma square, when mu is unknown. So now the mu is unknown. So we can't directly find the summation xi minus mu. So that is summation xi minus x bar can be taken. Okay. So summation xi minus x bar and the mu is unknown. So there is a lack of 1 degree of freedom. So s square is involved in our construction. So the confidence interval is our n minus 1 s square on chi square alpha by 2 n minus 1. Again n minus 1 s square upon chi square 1 minus alpha by 2. Then minus 1 degree of freedom. Okay, the same approach. Since one parameter is unknown, so there is a lack of 1 degree of freedom, and chi square is not symmetric in nature. So alpha by 2 and 1 minus alpha by 2 is there. Okay, we can take the value of alpha by chi square alpha by 2 from the chi square table, and then s square is what? This square is upon 1 upon n minus 1 summation psi minus x bar whole square. So n minus 1 can be cancelled out. So instead of using summation xi minus mu, we can here it is square actually. Okay, xi minus mu, we can directly use s square if s square is given. Otherwise, xi minus x bar whole square divided by chi square alpha by 2 n minus 1. Okay, so these are the cases. There is one more case. This is the last case I'm discussing here. Confidence interval for difference of mean. Suppose we have two population. Xi follows normal, mu1 sigma 1. Yi's follow or yj's follow normal, mu2 sigma 2 square. So confidence interval for mu1 minus mu2. The difference to their mean. Okay. So is there any difference? So that can be calculated like here xi follow normal, mu1 sigma 1 square. Suppose m and yj follows normal mu2 sigma 2 square n. Okay. So in that case, like when sigma 1 square and sigma 2 square is known, let me write the case when sigma 1 square and sigma 2 square is known, then the confidence interval for the difference of mean is defined as like x bar minus y bar. This is the case. Then minus plus z alpha by 2 because it's known. Then sigma 1 square upon m because we have n samples related to the sigma 1 square plus sigma 2 square by. So this is the formula for the construction of the confidence interval for the difference of mean mu1 minus mu2. Okay. So in the same manner, when not known, then you can write the sigma 1 square and we can construct the confidence interval for sigma 1 square and sigma 2 square when we have like uh, mu is known and mu is unknown. Okay, so these are the topics. So these are the topic that has been covered in week 10. So anyone have any doubt up to this point, he or she may ask. Otherwise, we will solve some numericals based on all these topics. Okay. So anyone have any question? Okay, then let's solve some numericals actually. So the first question is, let x1, x2, xn, let x1, x2, xn be a random sample from a population fx. From population or a PDF, I can directly write the PDF from the probability density function fx theta such that fx theta is defined as like theta plus 1 x to the power theta when x lie within 0 to 1 and theta is actually greater than -1. Okay, this is a perfect or valid PDF. Now, since it is there is only one parameter, find the sufficient statistic for parameter theta. Okay. Simple question. We can directly use factorization theorem. Okay, so the factorization theorem states that the or the joint distribution, not likelihood actually, the joint distribution actually is directly constructed by producting like doing product of the f of xi theta. Okay, I from 1 to n. So that means what? That means product I from 1 to n. That is theta plus 1 xi to the power theta. From here, theta plus 1 to the power n, product of xi to the power theta. That can be written as theta plus 1 to the power n, product of xi whole to the power theta. Okay, up to this point, is there any problem? Anyone? So now we can compare this. Okay, this equation 1, compare this with like we can compare like as theta equal to g of px theta into hx. So we can find comparing, let me write it in equation 2. Equations, what we get, we can find out like this is a function of x and theta. So that means I can write it like this. G of tx theta is our theta plus 1 to the power n, product of xi whole power theta, and hx is our 1 because there is no function remaining x. Okay, so from here, then in that case tx is our sufficient statistics. So here tx is what? The here this function product of xi is the only function associated with the random sample x. So that means what? So this implies what? Tx, which is equal to product of xi is sufficient statistic for parameter theta. Is it okay? I'm just constructing a joint PDF, joint probability density function, and then we can write or try to write the functional form in this format as given in equation 2, and then compare and find out the estimator which is sufficient. Okay, so here you can see the product. The product of xi's are our sufficient statistics. Okay. In the next question, actually, writing 3 or 4 questions in the similar manner. So, like here, let x1, x2, xn are IID random sample from a exponential distribution. Okay. x1, x2, xn follows fx lambda, where fx of lambda is our lambda e to the power minus lambda x. Lambda is greater than 0, x is greater than 0. Okay. Then we need to find the sufficient estimator. Find the sufficient estimator for the parameter lambda. Okay. So what we can do, again, start from the factorization theorem. We can construct this like joint PDF, which is product of this, and then we can write lambda e to the power minus lambda x, which is lambda to the power n e to the power minus lambda summation xi. Okay. Again, comparing like this is a function of g of Tx theta and into 1, this is our hx. So from here, we can directly say Tx, which is summation of xi, is sufficient statistic for parameter lambda. Okay. So in one case, the sufficient statistics is product of the random sample, product of xi. And in another case, it is summation of xi. Okay. Usually you will get either product or summation or a function of these. Okay. Usually, not always. Usually. Okay. So this is the case. There is one more case. In these two cases, the support of the PD of the parameter of the random variable is independent of the parameter. Here, you can see the x. Sorry, the x is independent of parameter. Here again, you can see the x is independent of the parameter. So in this case, it can be calculated directly or very simply. Okay. Now there is one more thing. The next thing. What if the support of the random variable is dependent on the parameter? Like for example, let x1, x2, xn be IID random samples from uniform distribution with parameter 0 and theta. Okay. Now, if I say find the sufficient statistic for the parameter theta. Okay, this is the case. So in that case, we can solve like first, let's write the functional form, the PDF actually. It is 1 by theta when x lie within 0 to theta, and theta is obviously greater than 0 because here the it belongs to 0 to theta. That means theta is greater than 0 in this case. So this is our PDF. We can construct the joint PDF, that is product of I from 1 to n 1 by theta, which is our what? 1 by theta to the power n. Okay. There is no function. Okay. So this cannot be directly with restriction. Which kind of restriction? Xi is less than theta. This is the restriction also involved with this joint median. Okay. So we can define a indicator function here. So let's define indicator function. So with the help of this indicator function, we can write this as like what? 1 by theta to the power n, then an indicator function. And the value of the indicator function is either 1 or 0 with maximum of xi. Since x is less than theta, this implies what? Maximum value of xi is also less than theta. Okay, when this condition holds, then its value comes out to be 1, 0 otherwise. Okay, so this is the indicator function. Now, this condition holds, then we can find out this like this. So we can directly write like this, na? This into I, any value Tx which is less than theta. It is also any value which is less than theta. So the nearest value is y, xn. The nearest value here is xn. Now it is hx. And this is what? This is our theta function and this is our tx. So from here, what? 0, x1, x2, xn, theta. So the nearest value comes out to be like xn. Okay, this represent theta better as compared to the other xi's. Okay, so yes, in that case our sufficient statistics, which is tx is equal to xn, which is the notation for the maximum of xi. Okay, so this is the case when our support is dependent on the parameter on itself. Okay, when our when our random variable xi depends on the parameter, then in that case we say that it is the sufficient statistics. Okay, so we can solve product of xi as a sufficient statistic. We have seen the summation xi, and then the maximum of xi is our sufficient statistics. Okay, so these are the cases. There is one more case. What if I am taking a discrete random variable instead of continuous? So there is one more question. And that question is again the same. Let x1, x2, xn be a random sample from Bernoulli distribution. Okay. So it is from Bernoulli distribution, then probability that x is equal to x will be like theta to the power x, 1 minus theta to the power 1 minus x. And in Bernoulli, the value is either 0 or 1 and 0 otherwise. Okay, so this is the case. Now we need to find the sufficient statistics, or if I say find the uniformly minimum variance unbiased estimator. Suppose the question is to find the uniformly minimum variance unbiased estimator for the parameter theta here of the Bernoulli distribution. Then we have already discussed in the above that Rao-Blackwell theorem and the Lehmann-Scheffe theorem. If we have if we have a sufficient statistics which is complete as well, then any functional form of that or that function itself a MVUE of the parameter. So yes, we need to first find the sufficient statistics. Then from sufficient statistics, we need to check whether that sufficient statistic is complete or not. And then we can say whether that estimator is UMVUE or not. Okay. So we will solve step by step. Okay. The first thing is to find the sufficient statistic. Okay. So yes. Again, the same. The joint PDF. The joint PDF is like written as product of probability that x is equal to xi, I from 1 to n. Okay. So it is like what? Product of theta to the power xi 1 minus theta to the power 1 minus x. Okay. So theta to the power summation xi 1 minus theta to the power 1 minus summation xi. It's not 1 minus, it's n minus. N minus summation xi, because summation over 1 minus xi is n minus summation xi. Okay. So we can write it like this: theta upon 1 minus theta to the power summation xi, because it's minus this, so that can be going to denominator parts, then 1 minus theta to the power n. We can write like this. Okay. So from here, we will compare again. This is the function of g of px and theta. And since there is no other term, so we can take hx equal to 1 as the function of x alone. Now the next step is here. This is the only function of random sample xi. So this is our sufficient statistic. Okay. So from here, px, which is equal to summation of xi, is sufficient statistic for parameter theta. Okay. So that means we have calculated the parameter, the sufficient statistic for the Bernoulli parameter theta. Okay. Now the next step is to check that is it complete or not. So that can be solved by the definition of completeness. So the second is let me write the completeness. Okay. So since t equal to summation xi is sufficient for Bernoulli, for Bernoulli parameter, this is the case. Okay. So the next thing is the distribution of t. What is the distribution of t? The distribution of t actually binomial with the same parameter theta with since we are considering n samples, so it's n. Okay, these have already discussed in the third week actually, if you remember. Okay, so Bernoulli n theta is our distribution for the t. Then now for the completeness, we need to show Like now, for the completeness property, we have to show that the expectation of HT equals 0 implies HT equal to 0. Okay. Or probability that HT equal to 0 is 1. Both have the same meaning actually. Okay. So what we can do, let's start with the expected value. So expected value of HT is like what? Summation I from 1 to n HT into probability that X. Here I can write T, okay, equal to T. So this is what? Summation HT. This is our, the T is our what? T is our binomial distribution. So the PDF is N C T theta to the power T 1 minus theta to the power N minus T. Okay. The simple definition of expectation. Now again, we can write like this. HT star. Let me write it HT star kind of thing if I want. And then theta upon 1 minus theta to the power N minus, sorry, this is direct T, no? Is T. And then 1 minus theta to the power N. We can write like this. Okay. Here H star T is our what? HT into NCT. Okay. Simple thing. I have clubbed these two and write H star T, and then the rest can be written in theta upon 1 minus theta to the power T multiplied by 1 minus theta to the power N. Now, everyone knows like this quantity, theta upon 1 minus theta, always positive to the power. Any value always gives a positive number. 1 minus theta, theta belongs to 0 to 1 because theta is a Bernoulli parameter. Okay. The probability of success. So always 0 to 1, yeah, excluding both, obviously. So this value and this value can't be 0. So this implies what? This H star T. This implies what? This H star T comes out to be 0. And yes, this can't be 0 again. So this implies what? HT comes out to be 0. Or probability that HT equals 0 comes out to be 1. So that means T. This implies, the next page, this implies T, which is equal to summation of Xi, is complete. Okay. T equal to summation Xi is sufficient. T equal to summation Xi is complete. Okay. So it is complete for parameter theta. Okay. So these are the three cases. Okay. The sufficient, the complete. Now the next is what? The Lehmann-Scheffe theorem. As Lehmann-Scheffe theorem states that if T is a complete and sufficient statistics, T is complete plus sufficient statistic, then HT is uniformly minimum variance and bias estimator for its expectation, like G theta equal to expectation of HT. Okay. Okay, so this is the case. Then HT is uniformly minimum variance unbiased estimator for, then HT is uniformly minimum variance unbiased estimator for G theta. So the next or the last step is to find the expected value of HT. Okay. So okay. The last step is expected value of HT. Okay. Expected value of HT, that is a function of T. So I have considered it by N. Okay. So which is 1 by N summation of Xi. T is what? Summation of Xi and 1 by N. So it is a function of T. 1 by N summation Xi. That is nothing but our sample mean. Okay. Up to this point. Now, as we know, the expected value of 1 by N summation Xi comes out to be 1 by N summation of expectation of Xi. Since Xi follows Bernoulli distribution, that is our question. Xi follows Bernoulli distribution. So obviously, it's 1 by N into summation. The expectation of Xi is theta, the P itself. Okay. So it is 1 by N into theta. So expectation of HT comes out to be theta. So that means what? HT is a UMB for theta. This implies HT is UMV of theta. Okay. So from here, that means the UMV of theta is X bar, which is equal to 1 by N summation Xi is the uniformly minimum variance unbiased estimator of the Bernoulli parameter theta. Simple. So the UMB of this is a functional form of sufficient statistics. Okay. So I hope up to this point everything is clear. If anyone have any doubt, you may please ask here. Is it any question up to this point? Anyone?
No, sir.
Okay. So the next is we can solve some numericals based on confidence interval now. Okay. So the question is like let x1, x2 up to x36. Okay. Be a random sample from normal distribution with unknown mean mu and known variance sigma square, which is equal to 64. Okay. Now question is construct the 95% confidence interval for the mu parameter. Okay. Also, x bar is given as 50. Okay. X bar is given as 50 and sigma square is known, which is equal to 64. We need to construct the confidence interval for the parameter mu. So the question is simple. Now the solution. Solution is like we are given since sigma square is known. So the confidence interval for mu at alpha level of significance is defined as like what? X bar plus minus Z alpha by 2 sigma by root n. Okay, this is the basic formula. Now we are given the value of X bar given X bar equal to 50. Okay, and sigma square is equal to 64 implies sigma equal to 8. N equal to, actually we are given 36 sample. Okay, so that means N equal to 36. Alpha equal to, like here we are given 95%. So alpha equal to like 0.05. So alpha by 2 obviously 0.0. Is there any question? 0.025. Okay, so these are the question. Now Z at 0.025, this value is for two tail. For two tail, this value comes out to be 1.96 actually. Okay, if you will see the Z table, you will find the Z value at 95% confidence interval for two tailed case is 1.9. Okay, so these are the information we are given. So yes, let's construct the confidence interval now. X bar minus plus 1.96 times sigma, which is A by n under root n, which is 36. This is our like 50 minus plus 1.96. It's multiplied by 8 by 6. Okay, so it's 50 minus plus 1.96 multiplied by 1.33. It's 4 by 3, that is 1.33. Okay, now it's obviously the simple thing, 1.96 into 1.33 comes out to be approximately 2.61. Approximate value is 2.61. Okay, to two decimal place. Then after solving, you will find it's 47.39. And when you add, it's 52.61. So this is our interval estimate. Okay. So this is the 95% confidence interval for mu when the given values are listed there. Okay. That is 95% probability that the true value lie within this range. Okay. Any doubt up to this point? Okay. The similar kind of question again. A random sample of 25 observations a random sample of 25 observations from a normal population yields the observed statistics, yields the observed statistic X bar is 20 and the sample variance is 5. Construct the 95% confidence interval for me. Construct the 95% confidence interval for the parameter. Okay. So again, the same kind of question with the unknown value of variance. Okay. So like sigma square is unknown. So instead of using sigma square, we can use the estimate of sigma square, which is sample variance as a square. Okay. So the formula for CI is like what? X bar minus plus. Now the distribution is changed from Z to T. So it's T, and since T is also symmetric in nature, so we can write T alpha by 2. Okay. And since sigma square is unknown and we have n samples, so the n sample comes out to be n minus 1 degree of freedom. Okay. Multiplied by s upon root n. The same thing. Now, given, we are given some values actually. X bar is given as 20. S is given as 5. N is given as 25. And yes, T alpha by 2. Okay. So T alpha by 2, that is T alpha by 2 n minus 1, which is T 0 point. Here it is given 95% confidence interval. This implies 0.025 at n minus 1 degree of freedom. N is 25, so 24 degree of freedom. Okay. So this value is what? This value, when you will see the T table, you will find out it's 2.064 or 2.06. Okay. So this is the T value, okay, tabulated value. Now, these all values, X bar, it's 20 minus plus 2.064 multiplied by 5 upon under root of 25. Simple calculation, 20 minus plus 2.064 multiplied by 1, because under root 25 comes out to be 5. 5 upon 5 comes out to be 1. So this is the case. So 20 minus 2.064 comes out to be 17.936, obviously, and it's 20 plus 2.064, 22.06. So this is our confidence interval for the parameter mu when sigma square is unknown. Okay. Any doubt up to this point? Okay, then. So we will solve some more numericals then. Okay. So the one more question is like, let x1, x2, xn be a random sample of size 13. We are given let x1, x2, xn be a random sample of size 13 from a normal distribution with The parameter value is mu and sigma square. Okay. Now, if we are given some information, if summation of I from 1 to n, that is 1 to 13, obviously. From 1 to 13, let me write 1 to 13. This comes out to be 246.61, and summation of xi square, again from 1 to 13, comes out to be 4806.61. Then the question is find or construct the 90% confidence interval for sigma square. Okay, this is the case. Okay, so here in this question, mu is not given actually. Okay, when mu is not given, so which distribution is used then in that case? Just try to remind uh, which distribution is used and how to proceed in this case. We need to construct the 90% confidence interval for the variance sigma square when mu is unknown. That case, simple. So, like confidence interval for sigma square when mu is unknown. Okay. So, obviously, you remember that it's n minus 1 s square upon chi square alpha by 2 with n minus 1 degree of freedom to n minus 1 s square chi square 1 minus alpha by 2 with n minus 1 degree of freedom. This is the uh, this is the formula for the construction of confidence interval. Now we do not give the direct value of these, so we need to construct. The first one is x bar 1 by n summation xi. Obviously, n is given as 13. Then summation xi is given as like 246.61. So x bar comes out to be, after solving, 18.9. Okay. Now s square, which is what? Which is 1 upon n minus 1. Summation of xi minus x bar whole square. So obviously it's 1 upon 12. So we will solve like put the value at last. Summation. Start with the expansion of quadratic formula, the a plus b whole square. So it's like what? Xi square plus x bar square minus 2x bar xi, taking summation on all values. It will be like summation xi square plus summation x bar square comes out to be minus 2x bar summation xi. Okay. So obviously it comes out to be like summation xi square plus summation x bar square is from 13. Let me write in general form n. So it is n x bar square minus 2 x bar. Summation xi is what? Like since x bar equal to since summation xi upon n comes out to be x bar. This implies nx bar equal to summation xi. Okay, so we can directly use summation xi is like nx bar. So this comes out to be 1 upon n minus 1 summation xi square plus nx bar square minus 2 nx bar square. So the overall formula will be 1 upon n minus 1 summation nxi square minus nx bar square. Okay. So this is the case. We can put the value directly here. Okay. So the value is like 1 upon n is 13. So 13 minus 1, that is 12. Summation xi square is given here 4806.61 minus nx bar square, that is already we have calculated now, which is 246.61. It is given, summation x bar. Sorry. That is the value of summation xi. Okay. That is given 13 into 18.97 whole square, x bar whole square. So this is the case. Now it's 1 upon 12. You need to solve this. There is nothing. 4806.61 minus this value comes out to be 4678.19. After solving, you will find this. Okay. Then, yes, 12 times of s square, because this is s square. So 12 times of s square comes out to be, the difference is 128.42. So this is actually n minus 1 s square. So I am directly not going to solve this anymore. So this is the case. Now the next is what? Now the next thing is, we are given alpha equal to 0.1 here. Okay. So alpha by 2 comes out to be 0.05 and 1 minus alpha by 2 comes out to be 0.95. Okay. Now from the chi-square table, chi square at 0.05 and n minus 1 degree of freedom is 12 degree of freedom. This value is actually 21.03 and chi square 0.95 at 12 degree of freedom comes out to be 5.23. Okay, so this is the value. Now putting all those values in our formula, that is n minus 1 s square upon chi square alpha by 2 n minus 1 n minus 1 s square upon chi square 1 minus alpha by 2 n minus 1. Okay. So n is equal to 13. 13 minus 1 comes out to be 12. So 12 s square value is 128.42. So it's 128.42 divided by 21.03. And then again 128.42 divided by 5.23. So our confidence interval will be like 6.11 to 24.5. So this is the confidence interval at 90 level, 90% confidence. Sorry, this is the confidence interval at 10% level of significance or 90% confidence interval. Okay. So this is the case when we do not know the value of mu. There is one more question. Up to this point, any question? Anyone have any doubt? No? Okay, then we have some more questions, like in a sampling from a distribution with a variance of 16, in a sampling from a distribution with a variance of 16. Okay. How large must the sample size be? How large must the sample size be so that the length of a 95% confidence interval for the mean is 1.9. Okay. The question says that we are given actually length, the length of the confidence interval, which is given as 1.96. Okay. And we are also given the variance. The variance is also given, which is 16. And this confidence interval is constructed for the mean mu. Okay. Then what will be the sample size for this condition? Okay. This is the question now. So let's start to solve this question. Okay. So here, like what we are given, sigma square is 16. Okay. So that means known. Okay. It is known. Also, like then sigma comes out to be 4. Simple thing. Okay. The next is in this condition, the confidence interval will be like x bar minus of sigma by root n and z alpha by 2. So x bar plus sigma by root n z alpha by 2. This is the formula when we know the variance. Okay. So the interval, what is interval length? Also, we also know that because it is telling a 95% confidence interval. So we know that the z value at alpha by 2 at 95% confidence interval comes out to be 1.96. Okay, simple. Up to this point, it's okay. Now, the next is length. Okay, suppose L is stand for the length. Length is what? The upper limit minus the lower limit. Okay, the upper limit minus the lower limit. So it's like x bar minus z alpha by 2 into sigma by root n. Sorry, this plus no, minus x bar minus z alpha by 2 sigma by root n. So obviously it's x bar plus z alpha by 2 sigma by root n minus x bar plus z alpha by 2 sigma by root n. So the length will be twice of z alpha by 2 of sigma by root n. This is the case. Now we are given L equal to 1.96 equal to 2 times of z alpha by 2 into sigma by root n. We need to find the value of n here, and the rest of the values are given. So 1.96 is equal to 2 is equal to at z alpha by 2, the value is also 1.96. That can be taken deliberately so that it will cancel out. Okay. Into sigma value is comes out to be 4 and then root n. So obviously this cancel out with this one. So it's 1, or let me write it directly. These are simple calculation. Root n comes out to be 8. Na? 2 into 4 comes out to be 8 simply. So from here n equal to 8 is square. N equal to 64. So the required sample size must be 64. For that, the interval length at 95% confidence level at for the mu is having the length 1.96. Okay, with variance 60. So it's simple. Any doubt up to this point? Anyone? No questions? Okay, then we have one more question. Okay. We have one more question actually. This question is like this is we are given two samples of size 16 and 10. Two samples of size 16 and 10 respectively are drawn at random from two normal population. If their standard deviations are 25.2 and 20. If their standard deviations are 25.2 and 20, respectively, then find 98% confidence interval for the ratio of the population standard deviation. For the ratio of the population standard deviation. Simple. This is given, and we need to now construct the confidence interval for the ratio of the population standard deviation at 98% confidence level. Okay. So let's start solving the numericals. What we are given two samples, obviously. So the first sample have the N1 equal to 16 and N2 equal to 10. Okay. And the corresponding S1 square is equal to 25.2 and S2 square is equal to 20. This is given. Okay. Now the confidence interval for the population proportion, for the proportion or the ratio of the population standard deviation. The confidence interval for the ratio of the population standard deviation is actually like this. Okay. The CI for sigma 1 square, sigma 2 square. This is the ratio. Okay. It's S1 square upon S2 square, f of 1 minus alpha by 2, 1 minus alpha by 2, it's N2 minus 1, N1 minus 1. 2 S1 square upon S2 square, f alpha by 2, N2 minus 1, N1 minus 1. So this is the formula for construction of the confidence interval. Okay. Now we are also so confidence interval for sigma 1 upon sigma 2, because it's for sigma 1 square upon sigma 2 square, but what we are asking here, standard deviation, which is under root of sigma 1 square sigma 2 square. So it is obviously it's s1 square upon s2 square f of 1 minus alpha by 2 n2 minus 1 n1 minus 1 to again s1 square upon s2 square f of alpha by 2 n2 minus 1 n1 minus 1. Okay, this is okay up to this point. Now alpha equal to 0.02 it is given, so alpha by 2 comes out to be like 0.01, and 1 minus alpha by 2 is 0.99. Okay, now you need to see the f table here, because f is there na? So f table is taken here. So f value at 1 minus alpha by 2, it's n2 minus 1 n1 minus 1 is what? It's 0.99. n2 minus 1 is 10 minus 1 9, 16 minus 1 is 15. This value is 0.202, and f value at alpha by 2 and 2 minus 1 and 1 minus 1 is f 0.01. 9, 15 comes out to be 3.895. This you can see from the F table. Okay, so these are at 99%, at 99, at 0.01, or the degree of freedom is 915 and 915 for both. Okay, so we have all the information now. Now the next thing is to put these value and evaluate. Okay, so the EI for sigma 1 square upon sigma 2 square is for S1 square upon S2 square. Na? So it's 25.2 divided by 20 multiplied by it's 0.202. And again, these 25.2 divided by 20 multiplied by 3.895. Okay, so this is the case. Now, the simple thing is to calculate these value, which comes out to be, it's 1.26 multiplied by 0.202. Again, 1.26 multiplied by 3.895, which is again comes out to be the root of 0.2545. And it's our 4.9077 approximately. And yes, you may solve this value and you will find out 0.5044 to 2.215. Okay. So I hope up to this point everything is clear. Is it okay up to this point? Okay, so this is the confidence interval for the ratio of the standard deviation. Okay, ratio of the population standard deviation when these are the sample values and these are the details. Okay. So up to this point, if anyone have any doubt, please ask. Anyone? Is it visible now?
Yes, sir.
Okay. So if there is no doubt or no question, I think I have done with all my questions here. Okay. So if there is no question, you people, then we can conclude our session here only. Is there any question? Yes, Murthy, I think you have one question. You may ask. Okay. If you want to ask any question, then you can ask here directly, no? Because I'm not able to see anything. Okay. Is there anyone who have any question? No. If not, then we can conclude our session here only. Okay. Then thank you, everyone. You may leave the session. Before that, let me stop the recording.